Human beings are now adding CO2 to the atmosphere at a rate that, to the best of our knowledge, is much faster than ever seen in the past. And based on geological records, the concentration today is well above anything seen for several millions of years. What evidence is there to support these claims? Join us as we explore how scientists map nature's historical impact, and in doing so, allow us to better understand the influence humans are having today. Mapping climate history requires the perspective of long periods of time, like the last 500,000 years. On that scale, one of our best natural history books is Glacial Ice. Ice retains signatures of the average climatic conditions at the time the snow fell, and it is the job of the climate scientist to collect ice samples, analyze these signatures, and reconstruct the climate of the past. To accomplish this, climate scientists need to travel to the far south, to Antarctica. Welcome to Epica and to Vostok, where the coldest temperature on Earth has been recorded, minus 89.2 degrees Celsius. These are among the best sites for long-term records of climate history. Vostok is a Russian scientific station in Antarctica, and Epica is a nearby European site. Both sit at high elevations on the Antarctic ice cap. Vostok Station is known in the scientific community as the site of a 3.6-kilometer long drill hole through the Antarctic ice cap, which, thanks to a joint Russian-French scientific collaboration, recovered an ice core that spans several 100,000 years of Earth history near the South Pole. Each section of the ice core brought up to the surface by the drilling crew is like the chapter in a book of climate history, with younger ice at the top and older ice at the bottom. Thousands of measurements of many different parameters are made on such ice cores, and since the late 1980s, the resulting data have yielded extraordinary new insights into the history of climate. We will explore two key properties that can be measured in the ice: the relative change of temperature through time and the concentration of carbon dioxide in the Earth's atmosphere over the last nearly 500,000 years. Let's look first at temperature history. Scientists can measure in ice the relative change of temperature at which the original snowflakes formed. Research shows that for about the last 10,000 years, the temperature was relatively stable at Epica and Vostok. It really didn't vary much over that time. Records from many other sites, including ice cores in Greenland and sediment cores collected from the seafloor and lakes, also confirm that the warm, relatively stable conditions were of global extent. Going farther back in time, or from right to left on this graph, note the steep decline in temperature between 10 and 20,000 years ago. This takes us back into the last ice age, which was at its maximum about 20,000 years ago. Note that the vertical axis is the temperature change relative to the average present-day temperature at the two sites. It is cold near the South Pole today, but during the last ice age, the average temperature was even colder, by about another 8 degrees. More importantly, a look at the entire record makes it clear that warm conditions have been relatively rare over the last 500,000 years. Cold glacial periods, tens of thousands of years long, have dominated, and these have been interrupted by warmer interglacial episodes that have persisted only for several to 10 or 20,000 years. You can see that over the last 500,000 years, each glacial-interglacial cycle has been roughly 100,000 years long. The data indicated by the red curve at the bottom come from a different source, namely the analysis of changes in the composition of tiny fossils retrieved from deep-sea sediment cores. These compositions vary only slightly as water is removed from or added to the ocean, as ice sheets on the continents grow or decay through time. Thus, the compositional changes in the marine fossils record the volume of continental ice through the ages. The close correspondence between the global ice volume record, shown in red, and the Antarctic temperature history, shown in blue and green, provides clear evidence that Mother Nature has caused dramatic, cyclical changes in Earth's climate for many hundreds of thousands of years. The question now is, how did she do that? Perhaps surprisingly, the answer lies in physical changes in our solar system, an idea first proposed back in the 19th century. In 1874, a very smart, self-educated Scot named James Croll wrote a beautiful little book called climate and time in their geological relations. He suggested that long-term cyclical changes in the Earth's orbit around the Sun through time would alter the amount of sunlight reaching planet Earth, and that times when less sunlight reached Earth could plunge us into a glacial period. Kroll's hypothesis was the first coherent attempt to explain why there had been multiple ice ages on the planet in the relatively recent geological past. About 40 years later, a young Serbian civil engineer named Milutin Milankovic declared that his life's work would be to pick up where James Kroll had left off and show mathematically that there was an astronomical origin for ice ages on Earth. Milankovic based his calculations on solar system physics, as defined earlier by giants in the field of celestial mechanics like Johannes Kepler. Milankovic explored the influence of three primary characteristics of the Earth's orbit around the Sun. Eccentricity refers to the fact that the Earth's orbit around the Sun is not circular, but follows an oval or eccentric track that varies from being more circular to less circular and back again on time scales of 100,000 to 413,000 years. A second feature, shown at the bottom right, is based on the fact that the Earth's axis is not vertical relative to the plane of the orbit, but is in fact tilted. The angle of tilt varies through time between 22 and 24.5 degrees. This nodding up and down changes the relative distribution of sunlight across the surface of the Earth on a seasonal basis, leading to hotter or colder summers or warmer or colder winters. One full cycle, from down to up and down again, takes 41,000 years. And finally, the Earth's axis also wobbles, an effect we call precession, just like a child's top as it slows down. That affects the relative lengths of the seasons on cycles that are 19,000 to 24,000 years long. Milankovic put all these influences together and determined that they change the amount and distribution of sunlight on the Earth through time. Like James Kroll some 6 decades earlier, he concluded that large ice sheets in the northern hemisphere, where most of the continental area exists on Earth, waxed and waned in response to this celestial forcing. Subsequent research has shown that he was right. The Milankovic cycles, as they are now known, clearly explain why we have had repeated ice ages on Earth roughly once every 100,000 years in recent geological time. Many decades later, we can now compare temperature changes through time at Vostok directly with variations in sunlight received by the Northern Hemisphere. Such a comparison reveals a remarkable correlation. Shown here are changes in average temperature at Vostok over the last 250,000 years. Similar temperature histories are seen in other records across the face of the planet, confirming that the Vostok temperature history is a proxy for global-scale glacial-interglacial cycles. Also shown in the blue curve is sunlight received through time in July at the latitude of Iceland. The correlation is remarkable and reinforces that changes in the Earth's orbit about the Sun act as a pacemaker for global climate changes over long time periods. In the past, Mother Nature was in charge, but that's not true anymore. Mother Nature is no longer exclusively in control, because human activities have now fundamentally changed the dynamics of how climate behaves on this planet. The slight long-term cooling that you can see over the last 9,000 years on the right side of this graph has been reversed now, and we know we are in for a substantial and very sharp warming if we continue to add greenhouse gases to the atmosphere. And what about those greenhouse gases? As we've seen, continental ice sheets yield a remarkable archive of temperature change on Earth. But glacial ice has another aspect that yields an equally extraordinary history: the composition of the Earth's atmosphere. This image is of a very thin slice of glacial ice viewed with a microscope through polarizing filters. Multiple ice crystals are shown by the various colors. Bubbles of trapped air are present at many of the ice crystal boundaries. The air was trapped as the original snow that fell onto the surface of a glacier was compressed gradually into ice. Analysis of that air down in the core gives us the composition of the Earth's atmosphere in the past. Scientists have been making such measurements for about 30 years now, and the results are absolutely spectacular. They indicate that atmospheric carbon dioxide content in the Earth's atmosphere is closely tied to temperature. Higher carbon dioxide concentrations are associated with warmer conditions on the planet. But correlation is not necessarily causation. So what is this information actually telling us? Careful analysis shows that at the ends of ice ages, there is a staggered sequence of changes. Temperature increases over several hundred years before the carbon dioxide concentration rises. That initial temperature rise appears to be driven by the Milankovitch cycles. More received sunlight begins to warm an Earth that is mired in the depths of an ice age. The warming ocean then releases CO2 because gases are less soluble in warm water than in cold water. That's one reason we keep champagne on ice. The newly released CO2 then drives up the temperature by just a little, but that has a big impact because it allows the atmosphere to hold more water vapor. Water vapor is an important greenhouse gas. The water vapor feedback loop is a major amplifier for warming. The ice core records show that this full sequence takes about 10,000 years, from its initial triggering by Milankovitch to the time when we reach a full interglacial period. This is an example of Mother Nature changing climate. Nature took 10,000 years to drive the carbon dioxide content in the Earth's atmosphere from about 200 parts per million during ice ages to 280 parts per million during interglacials. Human beings are now adding CO2 at a rate that is 300 times faster. In fact, its trajectory on the Vostok timescale, shown by the thick red line, is essentially vertical. As far as we can tell, such a rate of increase, sustained over decades, is unprecedented in the history of the planet. The concentration today is well above anything seen for several millions of years, based on geological records. The message here is clear. Based on the two properties of ice core samples that we have examined, the relative change of temperature through time and the concentration of carbon dioxide in the Earth's atmosphere over the last nearly 500,000 years, we see that Mother Nature does in fact influence climate. There is a correlation between CO2 concentrations in the atmosphere and temperature. And thanks to human activities, the concentration of CO2 in the atmosphere today is well above anything observed in geological records going back several millions of years.